Hello everyone. We are now in a stage where we have studied many of the initial concepts related to semiconductor physics. We started with semiconductor materials. Then we also have studied what is semiconductor material types, different types of semiconductor material. We also have studied in different types how do we classify those semiconductor materials in different ways. Then we have seen what is carrier concentration, how carrier concentration is different in intrinsic semiconductor as well as extrinsic semiconductor. We have seen how semiconductor physics has evolved and different considerations has been taken into account. For example, Fermi-level approximations like Boltzmann approximation, approximations like parabolic approximation as far as the density of states are concerned, and then how these approximations are helpful for us to simplify some of the situations. What is equilibrium? What is steady state? How equilibrium is different from steady state? Why one should consider equilibrium? Why one should consider steady state? And now in this particular lecture, we will discuss the concept Fermi-level only, but in intrinsic semiconductor. So the idea is how Fermi-level is placed inside an intrinsic semiconductor. So doping has an influence, or it actually changes the Fermi-level inside the material. The moment you create an extrinsic semiconductor, the position of the Fermi-level will be different. But before we go to that, it is very important that we understand that in an intrinsic semiconductor, where exactly this Fermi-level is placed. Once we know this conceptually as well as in terms of mathematical equation, if we know this, then only we can take a step further to understand what is the position of Fermi-level in extrinsic semiconductor. The moment you make an extrinsic semiconductor, the entire thing or the entire concept becomes little complex, because then there are multiple parameters that comes into the picture. For example, if you make an extrinsic semiconductor, the doping, the level of doping, the amount of doping, the dopant molecule, whether it is p type, whether it is n type, all these considerations will come into the picture. And we can only think about those considerations if we know that when these are not present, where exactly our Fermi-level is. And as I have mentioned in the previous lecture also, that Fermi-level is a very important concept. In many cases, this is the starting point of explaining a semiconductor device or explaining a semiconductor material or junction, so on and so forth. So in this lecture, we will now see how Fermi-level is placed inside the intrinsic semiconductor.
This is what we discussed in the last lecture. I'll just quickly go through this because it's very important in this lecture as well. So in the last lecture, we were figuring out what is the expression for Ni, that is intrinsic concentration. And this can be written as Ne into d, and which is a density of states function. And then you have the fraction that is occupied by the electrons. Now, in order to achieve the expression, we have taken three different approximations. So one is the ET is infinity. We have considered the value of ET, or replaced the value of ET rather with infinity. Why did we do that? One of the major reason behind that is if you look at the plot, then you have EC here and the FET function, it drops to 0, almost to 0 before it reaches ET, right? So even if you put ET, even if you put infinity in the place of ET, that won't create a significant difference. So you can replace ET with infinity, because that doesn't actually affect the result. Well before this ET value, your FET function is almost 0, right? Then the second one was Boltzmann approximation that you have taken into consideration. And the third thing is the probabilic density of states approximation. What does that mean? It means that the density of states function NE here, the value of, or the expression for NE we have taken as parabolic in nature near the edge of EC and EB. Okay. So if you look at the band diagram, this is your vacuum level. Then you have conduction band, the top edge. Then you have conduction band bottom edge, which is of our interest. Then you have valence band top edge, which is of our interest. Then you have valence band bottom edge, right? Then if you plot the NE function after taking parabolic density of states approximation, it will be something like that in the valence band. So it will be something like this, as it is shown over here. And total number of states in this case for a silicon crystal will be 4, which is the number of valence electron present in a silicon atom, into total number of atoms per centimeter cube, which is 5 into 10 to the power 22 per centimeter cube. Is that clear? This is the total number of atoms per centimeter cube, and then you have total number of valence electrons per atom. Remember, total number of states, allowed states in case of silicon atom is 8, because you have 3s2 and 3p6. These are the outermost orbitals for silicon atoms. So you can see total 8 states are available. However, we only have 4 electrons in those outermost shell. That's why 4 into 5, or number of atom, is your total number of states in the valence band. In the valence band, you have total number of states, which is equal to 4 into 5 into 10 to the power 22. And rest of the 4 is in the conduction band. We have discussed all these things previously. Now in this case, if you look at the conduction band density of states function, so as we have said, the entire function from EC to ET might be very complicated. It will not be as simple as the valence band one that we have shown here. But near the edge, we can consider a parabolic function. That is what our interest is. We will not look into the entire band, entire conduction band. Rather, our major interest is near the edge of both the bands, the lower or bottom edge of conduction band and the top edge of valence band, that is EC and EB. Now, if you draw the Fermi-Dirac function, which is FET in here, it will be something like this, green curve, right? So it will be something like this, green curve. So you will have this curve FET, and then you have NE over here, Okay. Now the total function, if you want to figure out, what you do, you take a d interval in this entire range and then integrate the same thing over EC and ET interval. Then you integrate the same from EC to ET. That is what has been done over here. And then you have applied the approximation and finally you get an expression like this for Ni. Okay. So if you take Boltzmann approximation, your FET value will reduce to this function. So in the entire Ni expression, the first part can be considered as NC, or we term it as NC, and the rest is basically the Fermi function under Boltzmann approximation. So we can write F suffix B into ECT, right? Why EC? Because we are considering this function in the conduction band near EC. That's why F into EC, comma T. All right. Now this NC, this value is basically the effective density of states at EC, that is at the edge of conduction band. This NC actually represents the effective density of states near that EC range, as if it is a delta function like this. The assumption or kind of consideration in this case is the entire density of states are concentrated in or near the EC only, near this level only. The entire states are concentrated, entire density of states are concentrated near the EC only. That's why the expression that you get in this case, also known as an effective description. What does that mean? An effective description? This might not be actual, but this is the effective description of concentration. Okay. Now, let us find out where the Fermi level is in the band. Okay. So as of now, we have seen the expression of Ni, but we do not know where the Fermi level is. Although we know there is a energy level which is known as Fermi level, below which at T equal to 0, all the available states are occupied. Above, the same thing at T equal to 0, all the states are unoccupied. But where that particular state is, that we don't know in the band diagram. The entire band diagram, as of now, we don't know where EF is. This is very important because I have drawn this curve, right? I have drawn this Fermi-Dirac function. However, without knowing the EF, you basically do not know where this function is, whether it is like this or it is like this, nobody knows. That's why it is very important to first figure out where the Fermi function or Fermi energy level is. To achieve that, what we have done, we have taken a different approach. Now, in order to get this, we will consider different possible options, and then we'll see, based on the concepts that we have studied or based on the logics, whether these options, these probable options are correct or not. The moment we find that the concept that we have studied or the understanding is not supporting one probable option, we will rule it out. Now let us take case 1. In case 1, what we have assumed is the Fermi level is actually inside the conduction band, that is somewhere in between EC and ET. Or let us take EF or Fermi energy which is higher than EC, as it is shown over here. Now, if this is the case, then let us see whether this particular case is supporting the kind of concept that we have studied previously. Now we have studied at t equal to 0, all available states above EF are unoccupied, which is true in this case. All available states above EF are unoccupied at t equal to 0. That is true because most of them will be in the valence band, right? All the electrons will be in the, just remember this energy state that we have discussed in terms of atomic separation. We said that the 4n states that are occupied are actually in the valence band, right? So at t equal to 0, all the available states above EF are unoccupied, which is true. But all the available states below EF are occupied. That is not true. Because there are states above EC in this case. If you look at this, there are states which is above EC below EF. Now, any states above EC should not be occupied at t equal to 0. That we already have studied. At t equal to 0, there should not be any free carriers, right? Because there is no generation. If there is no generation, there is no carrier in the crystal. No free carrier in the crystal means EC, that is conduction band, is now empty. So this particular statement that all available states below EF are occupied is not true. That's why this particular assumption is not true if we consider the concept that we have studied at t equal to 0. Similarly, let us go to the next case wherein we assume that EF is in the valence band, that is in between EV and EV, or EV and EV, somewhere here. Now in this case also, the first condition at t equal to 0, which is all available states above EF are unoccupied, is not true because in valence band all the states are occupied at t equal to 0. These states should be occupied, right? But as per the concept, all available states above EF should be unoccupied. But in this case, above EF, states are occupied. So this is also not true. So this is very clear that the Fermi energy function or Fermi level cannot be inside the conduction band, neither be in the valence band. So where it should be? It should be somewhere in the middle, in this band gap, right? The Fermi energy level should be somewhere in the middle, in between EC and EV. Now, where exactly it is? That much we already understood, that the Fermi energy level is somewhere in the middle or in between EC and EV. For that also, let us take one assumption that Fermi energy is very close to EC. Okay, let us take case 3 where Fermi energy is very close to EC. Now we know the expression of Ni, which is integration EV to EV, NED FET, that is the Fermi function, right? So this is the concentration or electron concentration in intrinsic semiconductor. Now corresponding hole concentration Pi will be integration EB to EB NED into 1 minus FET. For electron, if it is FET, for hole it will be 1 minus FET. That also we have studied previously, that for electron if it is FET, for holes it will be 1 minus FET, right? Let us plot both the function. Now I'm not again describing this equation because we have seen this equation multiple times so far. The analogous equation for hole is something like that, or something like the equation written over here. The only difference is FET will be 1 minus FET in case of holes, because if the Fermi function for electron is FET, for hole it will be 1 minus FET. Okay. Now let us draw these two functions, okay, FET and 1 minus FET. Now we already have seen the function FET previously. So if you have energy versus FET plot, then the Fermi function will look like the green curve over here. That is, it will be something like this. We have seen it. Now at EF, so this value should be EF, right? At EF, the function should be half. That also we have seen. We have calculated what is the value at E equal to EF. It should be 1 by 2. Now if FET is 1 by 2 at EF, what will be the value of 1 minus FET? It will be 1 minus half, that is half. So for 1 minus FET also the value should be half. And how this function will look like? This function will be kind of a mirror image or symmetric, but opposite if you consider this symmetry line at half, right? So this particular function will be something like this, shown in this graph. Okay. So this is 1 minus FET. Now let us go back to the band diagram again. Now this band diagram also we have seen many times as of now in different lectures. Now if this is EC, this is EV, we know that the density of states function near the edge will be parabolic, so it will be something like this, as it is shown in both the cases. That we know. So far we have seen many times. Then let us draw the Fermi function. In this case we know that Fermi level is near the conduction band, so we can draw a proper Fermi function in this case, because your Fermi function should be 1 by 2 at EF, that is shown over here. So if you draw the Fermi function, which will be similar to this green line, it will be something like, although it should be little this thing, but more or less it's correct. So the green line is showing the Fermi function. Similarly, you also plot 1 minus FET, so which is shown in this purple line, using this purple line in this plot. So you have both FET and 1 minus FET in this plot. Now the intersection in here is what your Ni, or the concentration of electron, is. Now if you look at both the areas, here and here, they are not same. They will not be same if EF is not in the middle, right? So if they are not same, under equilibrium, Ni will not be equal to Pi, right? That is not possible. Why? When Ni is equal to Pi, as per this diagram, Ni will be equal to Pi, that is both the areas will be same when you have a EF which is exactly in the middle of this band gap. And hence we can say that in case of semiconductor physics, the Fermi energy should be in the middle, exactly in the middle of EC and EV, right? So these two should be the Fermi energy level should be in the middle of EC and EV. Okay, so let us now see what is the value of EC minus EF. So this much is clear that your Fermi energy should be in the middle. So what will be the EC minus EF? This particular value will be half of the total value, because now your EF is in the middle. So your EC minus EF will be half into 1.1 electron volt, which is 0.55 electron volt. And what is the value of 3 kT? The value of 3 kT is 3 into 0.026 electron volt, right? Because kT value we already have seen at T equal to 300 degree Kelvin, or at T equal to 300 Kelvin rather. The kT is 0.026 electron volt. Now your 3 kT value will be 3 into 0.026 electron volt, which is 0.078 electron volts. Hence, your EC minus EF is always greater than 3 kT value. That's why Boltzmann approximation that you have taken previously is valid. We have taken here, right, the Boltzmann approximation. We have taken here Boltzmann approximation while calculating the Ni. The question was, how do we know that Boltzmann approximation is valid before taking? Now what we have done, we have calculated the entire expression. We have the expression right now. And now we are verifying that whether this particular condition is satisfied or not. We have seen that this condition is satisfied. Now see, even if your T value is very high, your Boltzmann approximation will always hold. In any practical value of T, if you take the real-time situation, if you take any real-time temperature, real-time as in real-life situation. If you take a real-life situation, and if you take any real-life temperature, this Boltzmann approximation or condition for Boltzmann approximation will be valid, because 0.078 is very less compared to 0.55, right? So even at T equal to, let's say T is equal to 900 Kelvin. So even if it is 900 Kelvin, your kT value, that is kT or K into 300 into 900 by 300, that will give you K into 900, right? Which will be K into 300 is 0.026 and this value is 3. That means another factor of 3 will be multiplied with this. If you do that study also, so 3 into 3 is 9, so it will be 9 into 0.026. Even if you consider 10, then also it will come 0.26, right? Even if you consider 10 instead of 9. I'm just giving you an idea, okay? Then also it will come 0.26, which is less than 0.55. I was talking about 900 Kelvin, which is in real life situation, it's not possible. It's very high, right? Then also your Boltzmann approximation will hold. That's why we can apply Boltzmann approximation in many of the cases that we study in this course. All right. So what we have studied, we have seen where the Fermi level is from a kind of a reasoning or a different kind of analysis, taking the possible situation and ruling them out by giving some reasoning or by giving some concepts. Okay. Then we figured out that EF should be at the middle of EC and EV in the band gap. It should be in the middle of the band gap. And then we also have seen that Boltzmann approximation will hold at any temperature. We just did this calculation. So whatever expression we get for Ni after taking Boltzmann approximation is okay or is fine. Now you have Ni, the expression for Ni, which is 2 into this value. Now similarly, you also can calculate the expression for Pi. The only difference will be your Mn will be replaced by M suffix P, and your Ec minus Ef will be replaced by Ef minus Ev. So please note, there is a minus sign here. So your Ec minus Ef will be always, your Ec minus Ef will be replaced by Ef minus Ev in case of Pi. You can do this in your home, but will be very analogous to the expression of Ni. So I have just mentioned the change change in this equation for Pi. So I have mentioned the change in this equation for Pi over here using this red color. Okay, these are the only changes. So I just put red ink for these changes so that it becomes easier for you to understand where exactly the parameters will change in case of Pi. Now let us multiply these two, Ni into Pi. So if you multiply these two, then you will get an expression like this. Now Ni into Pi can be written as Ni square, because for intrinsic semiconductor Ni is equal to Pi under equilibrium. So you just replace Pi by Ni, or you can replace Ni also by Pi, but let us take Ni in this case. It will be Ni square. This particular expression can be written as Nc into Nv. This is Nc. So this will be Nv. So what is the difference between Nc and Nv? The effective mass of electron and hole. Okay. Rest more or less is same, right? So you have Nc into Nv, and then you have exponential minus Eg, because Ec minus Ev is nothing but the band gap, which is Eg divided by Kt. So this is your final expression for Ni, which is equal to square root of NcNv into exponential minus Eg by 2Kt. In this case, most of the parameters you will find. Previously, there were values like Ec minus Ef. Now, in this case, you get an expression in terms of band gap. Okay. So this is another expression for Ni. Now, what is the dependence of Ni with respect to temperature? Because we have seen, if you increase the temperature, your Ni will also increase. So you have the temperature parameter in both these places, right? So let us see what is the dependence. So let us start from this equation, and then let us first take temperature out of this expression. So this will be Ni is equal to V into T to the power 3 by 2. This was Ni square, right? So if you square root the entire expression, it will be 3 by 2, right? So that's why it's 3 by 2, and rest expression will be considered as a constant B. That can be considered as constant B. So this is Ni is equal to B into T to the power 3 by 2 exponential minus Eg by 2Kt. Okay. So this is what you will get. So in this case, if you divide the Ni with a known value, say the value of Ni at 300 Kelvin, because mostly this parameter is known for different semiconductor material. What is the intrinsic concentration for a semiconductor at room temperature? So if you divide that with this known value, then it will give you an expression like this, and then you can use this expression for finding out what will be the concentration at different temperature. Now, why we did this? We did this to get rid of this constant B, because we don't know what is the constant B, because this constant, if we want to remove, then what is the easiest way? The easiest way is to divide the entire expression with some known values, or the other way could be you can calculate the value of B as well, but in this case you need to know many other parameters. So again, for the sake of simplicity only, we have done this. Otherwise, you can use this expression as well. Just figure out what is the value of B and do the calculation. However, if you do in this way, things will be much easier. You will get rid of the expression or get rid of the constant B, and then you have the entire expression ready, wherein most of the values are known. Okay, this is what is the dependence of temperature for NI. Now, let us see here also what is the relation between temperature and Ni, right? So, if you take log both the sides, it will be log Ni is equal to log B, which is a constant again. Then you have 3 by 2 into log T, and then you have minus Eg by 2K into 1 by T. So in this case, if you see your log Ni versus 1 by T plot will be more or less straight line. In fact, it will be straight line, because in this case, this term, the effect of this term will be very less. It will not be that visible. Okay, so you will have again a relation which is almost linear, and that is what you see in different plots that I have shown previously. And the slope will be Eg by 2K. So if you know the slope of this plot, you will get to know what is the value of Eg. In the plot that we have seen previously, Ni versus 1 by T, or better to say log Ni versus 1 by T, if you can find out the slope of that plot, you will get to know what is the band gap of the semiconductor. Okay, now from here you also can calculate the expression for Fermi energy. Just equate Ni and Pi. So we know under equilibrium Ni is equal to Pi. If you do that, you do it in your home, you'll find that EF is equal to EC plus EV divided by 2 minus KT into ln NC NV. Now, this NC and NV both are almost same. What is the difference? The effective mass, Mn and M suffix P, effective mass of electron and effective mass of hole. And both of them are not very different, almost similar. So your NC and NV you can consider to be very similar. So the entire expression, this expression, the second term of EF is very negligible compared to this. Hence, the entire thing will be reduced to EC plus EV divided by 2. Right? This will reduce to EC plus EV divided by 2. That is what your expression for EF. However, please remember there is a dependence of temperature in Fermi level as well. So at higher temperature, your Fermi level will go down. That one should remember. Although it is very small, but there is a dependence. If you increase temperature, your Fermi level will go down slowly, because this is this term minus this expression. So this particular term, as it goes higher and higher, your entire expression will go lower and lower. So your Fermi level will go down as temperature rises. However, we can comfortably neglect this term because NC and NV are very equal, very close to each other in terms of value, as they are almost same or approximately equal, we can neglect this term and the expression for EF remains EC plus EV divided by 2. That means EF is almost in the middle of the band gap. Okay.
So you can see that the position of the Fermi level inside the intrinsic semiconductor is right in the middle of this energy band. And we have taken an approach which is conceptual in the beginning to see whether this Fermi level should be within the band or in the valence band or in the conduction band, and that conceptual thought process is very, very important, because until and unless you visualize the entire process, or if you don't understand how conceptually this particular the particular situation has been explained, it becomes very unclear for someone to understand only from the mathematical equation. So we started with conceptual understanding, we started with a conceptual discussion, and then slowly we move to the mathematical equation to see how we can actually say the position of Fermi level from a mathematical equation also. Now it is very important that we remember this, because these considerations are very important and will be used in the subsequent lectures and device development and device design. With this, I will conclude this lecture, but we will meet again with more concepts in the coming lectures. Thank you.